Hi everyone, welcome to homework 4.7. Today we looked at revenue, and so that is when we're talking about how much a ticket is going to sell for and then the predicted amount of tickets we can sell at that price. So the people, discovered that based on past musical productions, a theater predicts selling 400 minus 8p tickets when each ticket is sold at p dollars. So if the ticket price is $5, they would sell 400 minus 8 times 5, which is 40, which would give us 360 tickets. So at $5 a ticket, they can sell $360. And so that would be 5 times 360 is 1,800. All right. So then you'll do the same thing for 10. If I plug in 10 here, I get 400 minus 80. So that would be 320. Then 320 times 10 will be 3,200. For 15, I can do 8 times 15 is 120. So 400 minus 120 gives me 280. And then 280 times 15 gives me 4,200. All right, so if I sell them for more at this point, I can still sell enough tickets that I'm making a decent amount of money. Right now, if I go up to $20 a ticket, 8 times 20 is 160. 400 minus 160 allows us to sell 240 tickets. 240 tickets times 20 gives us $4,800. All right, now at 30 tickets, $30 per ticket, 8 times 30 is 240, so 400 minus 240 gives us 160. And so at 160, we will, I'll make sure I did that correctly, 8 times 30 is 240, 400 minus 160. Yep, 160 times 30 gives me 4,800. Ooh, so we're still at the same amount there. If we were to do $45 a ticket, 45 times 8 is 360. So that would only allow us to sell 40 tickets here. And so if we sell 40 tickets times $45 each, we get 1,800. So notice we're going back down now because the price of the ticket has gotten too high. So if I do 50 times 40, $50 times 8 is going to give us 400, right? So 400 minus 400 is 0. So if we sell them at $50, we will no longer sell any tickets, which means we will have $0 revenue. So our equation would be P times 400 minus 8P. And then we would multiply these, which is our distributive property. So 400P minus 8P squared. Remember, P times 8P would be 8P squared. And so this is a quadratic function because now we have a squared term. It says, for which ticket prices will the theater earn no revenue? So $0, right? If they sell them for $0, we will earn no revenue. And at $50, we also earn no revenue because when we plug in $50, we would get 400 minus 50 times 8, which is 400. That equals 0. Right, so you can show me mathematically, and then similarly, if we charge $0, $0 times 400 minus 8p, anything times 0 will be 0. At what ticket prices should the theater sell the tickets if it must earn at least $3,200 in revenue to break even, not to lose money on the musical production? So if they want to earn at least $3,200, they could sell the tickets for $10. They could sell the tickets for $15 because they would earn more than that. They could sell even up to $20, right? Let's take a look at the equation in the calculator to see what is that greatest amount we would be able to hit before we start to go back down. So we have 400p minus 8p squared. So let's take a look at that. Let me clear this out. 400 x minus 8x squared, and graph. All right, so we cannot really see that graph because it is too zoomed in. So let me go ahead and adjust my window. I'm going to do, oops, let me do -1 here, just so I have a little bit of space on the side there. And the X max, we looked at as much as, ooh, $50 tickets. So let's do 50. And then the Y min, that's fine. We can keep that at that. Let's do a Y max of our max revenue. Let's do 5,000 and take a look and see how that graph looks. Oh, that's nice, right? So that gets us quite up to the tippy top. I'm actually going to do a little bit more than 5,000. Let's do 5,100 just so we have a little bit more space to work with at the top there. There we go. Now we can see the very top. All right, so I want to look and see what is that maximum value here. And so I'm going to do second calc. And let's do our maximum. And I'm going to move it a little to what I perceive to be the left and a little bit to the right there. And then our maximum is 25. So it looks like as much as $25 can get us a nice amount. However, then also, if I go to the right of that, right, so let's do trace so I stay on the line here. If I go to the right of that, as I go down, I'm looking to see where does the Y get below 3,200, because we want everything to be above 3,200, right? So that's going to happen right about here at $39, it looks like, between $39 and $40. So we're going to say from $10 to $10 to $39 gets us enough there, because 10 gives us 3,200 exactly. So from about $10 to $39, we still have over 3,200. So if they sell them for those prices, this range right here, oh, sorry, this range right here, right, will be above 3,200. All right, let's actually, and let me go ahead and type in, if I type in 10 here, x equals 10, I get 3,200. So that shows me pretty nicely, right? And then 39 gives me 3432. So I could do a little bit more than that, because if I go to 40, oh, we're at exactly 3,200 actually. So 40, so let's say to 40 works, okay? We could see that in between that 30 and 45. All right, a company sells running shoes. If the price of a pair of shoes is 30 in dollars is P, the company estimates that it will sell 50,000 minus 400 P pairs of shoes. Write an expression that represents the revenue in P dollars. So this would be P times the number of shoes that we can sell. And so that gives us 50,000 P minus 400 P squared is our equation. So we can say our revenue equals 50,000 P minus 400 P squared. All right, number 3, the function F represents the revenue in dollars a school can expect to receive if it sells 220 minus 12x coffee mugs for X dollars each. Here's the graph. So we're assuming that they've done X times 220 minus 12x, which is 220x minus 12x squared. At $2 per coffee mug, the revenue will be $196. So $2 will be here. That looks to be, this is 300, so that's more than $196 of revenue. That is not true. The school expects to sell 160 mugs if the price is $5 each. So $5 each would put us at $800 in revenue. If we have $800 in revenue, right, 160 mugs, for $5 we would get 12 times 5 is 60. 220 minus 60 is 160. So that is true. Okay, so for 160 times 5 is 800. And so we can see when we sell 5 mugs, we're at the 800 point here. The school will lose money if it sells mugs for more than $10 each. So at this point, if we get to $10, the school revenue is going down. So the school, it's not really that they'll lose money, it's that they'll earn less money. I wouldn't say lose money, but they will earn less money if they sell them for more than $10 each. So this is like a kind of. The school will earn about $1,000 if it sells mugs for $10 each. So $10 each here is about $1,000. That's true. The revenue will be more than $700 if the price is between 4 and 14. So if the price is between 4, let me erase these other points just so it's easier to see. 4 and 14. The revenue will be more than $700. So at 4, it honestly looks like it's just under 700. Let's take a look. Yeah, that is just under 700. So I'm going to say no. It would need to be a little bit more than 4. Maybe if we were to say 5, or even like, I mean, honestly, like 4.25. The expected revenue will increase if the price per mug is greater than $10. So if the price per mug is greater than $10, the revenue is going down. So the revenue will not increase. All right. Number 4 says, write an equation to represent the relationship between the step number and the number of small squares. So remember, we're looking at quadratic. We're looking to find the square. So let's mark out our squares. This would be 3 times 3 because we have step 3. And then notice here, I'm adding 1, I'm adding 4, I'm adding 9. So this means, in essence, I'm multiplying this times 2. All right, and so here the pattern would be n y equals n squared times 2, or y equals 2n squared. Both of those would be fine because we're multiplying that by itself. You could also say y equals n squared plus n squared, right? Because you're adding another n squared on top here. That will still give you 2n squared. They're equivalent. And so you can show me through your drawings how this relates to the pattern, or you can say that the 2 is multiplying the square pattern. Okay. Is the relationship between the step number and the number of small squares quadratic? Yes, because it has a squared term. All right. Number 5, a small marshmallow is launched straight up in the air with a slingshot. The function h is given by this equation, which describes the marshmallow in meters. So this is in meters, that's why it's not 16t squared, as a function times t in seconds since it was launched. Use graphing technology to graph the function h. So let's do that. 5 plus 20t minus 5t squared. So 5 plus 20x minus 5x squared. And then let me just get rid of that there. Ooh. Okay. All right. So we're going to graph that. Oh, it's very tiny. So let's adjust our window. Let's make our y max only 20 and see what happens there. That's a little too small. That's better. We can make it 30. And then let's make our x max smaller as well. Let's make that 20 and see if that helps a little bit. Ah, there we go. That's a bit better. So notice that our x values are going to 1, 2, 3, 4.5. So I can actually go ahead and make this window even smaller. Let's do 6. And then I can get a nice, better picture of my graph there now. Okay. So what about when does the marshmallow reach its maximum height? So here we're going to do second calc. We're going to look for our maximum. I want to go to the left of my curve here, enter, and to the right of my curve here, enter. And I get a maximum of 2. At 2 seconds, it is 25. So 25 feet. Oh, no, sorry, meters. We're doing meters in this case. It's important to pay attention to that. So 25 meters at 2 seconds. But how long does it take before the marshmallow hits the ground? So let's see, we want to see 1, 2, 3, 4. It looks like about 4.25, but let's go ahead and be more precise and calculate that 0. I'm going to move close, maybe. This is taking quite a long time to get there. All right. So left bound, enter, and then I'm going to go right bound, enter, have a guess, and it's 4.236, so 4.24, right? Yeah, 4.24 seconds approximately. And what domain makes seconds to the function h in this? So this would be from 0 to 4.24, or we could say x is less than or equal to 4.24 and greater than or equal to 0. Yep, that's our time that we're going to be putting in. Okay, number 6. A rock is dropped from a bridge over a river. Which graph could represent the distance fallen in feet as a function of time in seconds? So this is the distance fallen, right? Not how far it is from the ground, which means it should be increasing. So that helps me to eliminate graph B. It also helps me to eliminate graph D, rather, right? Because these show a decrease, but we're increasing the distance fallen. So it would need to be A or C. Now, generally speaking, when we're talking about something falling, it's going to include either 16x squared or 5x squared, depending on whether we're doing feet. I guess this is feet, so this would be 16x squared, which is a quadratic, so it should have a curve to it. So C makes the most sense in this situation. And again, that's because the distance fallen is increasing, right? As it falls, it's fallen more feet. If it were asking us how far is it from the ground, then we would be looking at a situation where it's decreasing because it's getting closer to the ground. Our last question, a bacteria population P is modeled by this function. So this is you should recognize immediately that this is a exponential function because it has the variable in the exponent. Select all statements that are true in this situation. 100,000 times 2 to the negative 2 represents a bacteria population 2 days before it was first measured. Yes, we have a negative exponent. It's referring to earlier time. The bacteria population 3 days before it was measured was 800,000. So in this case, it is doubling each time. So 3 days before it was measured should be less than 100,000. So we can just reason that that's not true. The population was 1,000 1 week before it was first measured. So 1 week would be 7 days. So let's take a look at that. If we do 100,000 times 2 to the power of negative 7, we get 781. Yeah, so it was not more than 1,000 1 week before it was first measured. The population was more than 1 million 1 week after it was measured. So same equation here. Times 2 to the power of 7 now is 12,800,000. So yes, that is definitely more than 1 million. And then letter E, the bacteria population 4 days before it was first measured. So 4 days, let's do 100,000 times 2 to the power of negative 4. Was it 4 days? Yep, is 6,250. So yes, that is true. All right, that's it for your homework. Your code word for today is let's do equator. Equator is your code word for today. Happy homeworking and see you tomorrow.